Welcome back, everyone, to the Deep Dive. We always talk about the cutting edge, the latest and greatest technology, but today we're going back to the basics, back to the building blocks. We're talking about algorithms.
Algorithms. Now, I know for some people that word might bring back some not so fond memories of computer science class.
Yeah, maybe a little bit of a head scratcher. But here's the thing. Algorithms aren't just some abstract concept. They're the engine driving pretty much every piece of technology we use.
Exactly. And this book, Introduction to Algorithms, 4th edition, it starts off by making that very point. Algorithms, they're everywhere.
Yeah, like literally everywhere. Think about it. Your microwave, your washing machine, your smartphone, they all rely on algorithms to function.
And it goes way beyond our devices, too. Think about the recommendations you get on Spotify or Netflix.
Or how about Google Maps figuring out the fastest way to get you home?
Even things like online shopping, the stock market, the systems that control traffic lights, they all depend on algorithms.
It's actually kind of mind-blowing when you stop and think about it. And as algorithms become even more integrated into our lives, understanding how they work, well, it's becoming more and more important for everyone, not just computer scientists.
That's absolutely right. The preface of this book actually points out that just having a basic understanding of what algorithms are, what they can do, and importantly, what they can't do, that's a really valuable skill in today's world.
So that's why we're here today. We're going to dive deep into this, the very first chapter of Introduction to Algorithms, 4th edition. And leading us on this journey are the authors themselves, Thomas H. Corman, Charles E. Liserson, Ronald L. Rivest, and Clifford Stein. These folks are the rock stars of the algorithm world.
Oh, absolutely. This book is considered the Bible of algorithms.
Right. In this first chapter, well, it really sets the stage. It gives you the foundational understanding of what algorithms are, why they're so important, and how they fit into the bigger picture of computing.
Basically, it answers the questions. What is an algorithm? Why should you care about them? And how do they actually work as a technology?
Perfect. So let's jump right in, shall we? Let's start with that first big question. What is an algorithm? I mean, we've thrown the word around a bit, but what's the formal definition?
Well, the book defines an algorithm as a well-defined computational procedure that takes some value or set of values as input and produces an output.
Okay. Input, process, output. Kind of like a recipe, right?
Yeah, you could think of it that way. You have your ingredients, which is your input. You follow a set of steps, which is your algorithm, and you get a final dish, which is your output.
And those steps, those have to be really precise, right? No room for interpretation.
Exactly. Every step needs to be clearly defined, unambiguous. The algorithm has to be able to take any valid input and produce a correct output every single time.
So it's not just about getting an answer, it's about getting the right answer consistently.
Exactly. And that's why algorithms are so powerful. They give us a way to solve problems in a systematic, repeatable way.
The chapter actually uses a classic example to illustrate this. The sorting problem.
Sorting. One of the fundamental tasks in computer science. We sort things all the time in our everyday lives.
Absolutely. Whether it's alphabetizing a list of names or arranging files in your computer, we're constantly sorting things.
And the book breaks down the sorting problem in a very formal way. You have an input, which is a sequence of numbers, let's call them A1, A2, A3, and so on. And your output is a rearrangement of those same numbers, but in a specific order, typically from least to greatest. So you have A1, A2, A3, but now they're in order.
Like if your input was the numbers 31, 41, 59, 26, 41, 58. A correct sorting algorithm would give you 26, 31, 41, 41, 58, 59.
Exactly. And that initial sequence, that 31, 41, 59, 26, 41, 58, that's what we call an instance of the sorting problem. It's basically just one specific example of a possible input.
In this sorting example, it really highlights how algorithms can be applied to real-world problems.
Absolutely. Think about databases, spreadsheets, online search results. Sorting is a key component in all of these.
And as the chapter points out, there are actually tons of different algorithms for sorting. It's not a one-size-fits-all kind of thing.
Oh, absolutely. And choosing the best sorting algorithm, that depends on a lot of factors. The size of your data set, whether the data is already partially sorted, even the type of computer you're using can all play a role.
So you've got your input, you've got your output, you've got your algorithm, which is the set of steps to get from input to output. But what makes an algorithm correct?
Well, a correct algorithm, it has to meet two key criteria. First, it needs to halt. This means that the algorithm needs to finish its computation in a finite amount of time. It can't just keep running forever.
Right. Makes sense. You don't want your computer just spinning its wheels endlessly.
Exactly. And the second criterion is that the algorithm needs to produce the correct output for every possible valid input. If it fails on even one input, it's considered incorrect.
So it's like if you're baking a cake, you don't just want the recipe to eventually stop. You want it to stop when the cake is perfectly baked.
Yeah, that's a great analogy.
Now, the chapter does mention that there are some situations where you might actually use what they call an incorrect algorithm.
That's right. There are some cases, particularly in areas like cryptography or very complex simulations, where you might use algorithms that don't always give you the perfect answer, but they might give you a good enough answer, and they might do it much faster.
So it's a trade-off between speed and accuracy.
Exactly. But for most everyday problems, we definitely want algorithms that are correct and efficient.
And it's also worth noting that algorithms can be expressed in different ways. It's not always lines of code.
Right. You can describe an algorithm in plain English, you can write it as a computer program, you could even express it as a hardware design.
The key is that the steps are clear and unambiguous, regardless of the format. Okay, so we've got a good grasp of what an algorithm is. Now let's move on to why we should care about them. And to illustrate this, the chapter goes into some fascinating examples of how algorithms are used to solve all sorts of real-world problems.
Yeah, and this is where it really gets exciting. We start to see how algorithms are not just some theoretical concept, but a powerful tool that's driving innovation in so many different fields.
And one of the most inspiring examples they give is the Human Genome Project.
Absolutely. I mean, this was a massive scientific undertaking. The goal was to map the entire human genome, all 3 billion base pairs of DNA, and it was algorithms that made it possible.
Right. Algorithms are what allowed scientists to process and analyze those massive amounts of data. And that led to all sorts of breakthroughs in medicine, genetics, and our understanding of human biology.
And the chapter even mentions that a technique called dynamic programming, which we'll cover later in the book, played a key role in things like figuring out how similar different DNA sequences are.
Wow, so dynamic programming is a technique used in genomics. That's amazing. It's really cool to see how these algorithms connect to different fields.
Right. It's all connected. And, another great example is the internet, something we all use every day, but probably don't think much about the algorithms that make it work.
Oh, for sure. I mean, the internet is essentially this massive network of computers all over the world, constantly sending and receiving data. How does all that information get where it needs to go so quickly?
Algorithms. Algorithms are what determine the best paths for data to travel across the network. They're what make sure that your emails, your web pages, your video calls all arrive at their destination quickly and reliably.
And then there's the whole world of e-commerce. We're constantly buying things online, sharing sensitive information like credit card numbers. How is all that kept secure?
Well, a lot of it comes down to cryptography, which is essentially the art of encoding information in a way that makes it very difficult for unauthorized people to access. And guess what? Cryptography is built on a foundation of mathematical algorithms.
So algorithms are literally what's protecting our online transactions. That's incredible.
It is. And it goes even further. Algorithms are used to detect fraud, to personalize our shopping experiences, to manage inventory, you name it.
They're like the invisible force behind the entire online economy.
And they're not just confined to the digital world either. The chapter also talks about how businesses and organizations use algorithms for all sorts of things, like optimizing supply chains, managing resources, even making strategic decisions.
You know, it's striking how diverse these applications are. And the chapter gives us a glimpse into some of the specific problems that are tackled in later parts of the book.
Right. It's like a little preview of the algorithmic toolbox we'll be exploring.
For example, they mentioned the shortest path problem. It's about finding the most efficient way to get from one point to another.
Yeah. Like if you're using a GPS navigation app, the app uses an algorithm to find the shortest route from your current location to your destination. And those algorithms, they're not just used for navigation either.
Right. They're also used in things like network routing, where you need to find the most efficient way to send data packets across the internet.
And another interesting example is something called topological sorting.
Topological sorting, that sounds a bit more abstract.
Yeah, it is. But it has a lot of practical applications. It's basically about figuring out how to order things when there are dependencies involved.
Dependencies, what do you mean by that?
Like, let's say you're assembling a piece of furniture, right? You can't attach the drawer handles until you've built the drawers themselves, and you can't build the drawers until you've put together the frame. So there's a specific order you need to do things in.
Oh, I see. It's about figuring out the right sequence of steps.
Exactly. And topological sorting algorithms, they can help you find that optimal sequence, especially when you're dealing with really complex projects with tons of steps and interdependencies.
So from mapping the human genome to figuring out how to put together furniture, algorithms seem to have a pretty wide range of applications.
They really do. And the chapter dives into even more examples like medical imaging analysis, data compression, all sorts of things.
And what really stood out to me is when they start talking about the common threads that run through a lot of these algorithmic problems.
Yeah, they point out two key characteristics that many of these problems share.
The first one is that there are often tons and tons of possible solutions, but most of them are either incorrect or just not very good.
Right. So the challenge is to find that needle in a haystack, that one solution that's both correct and efficient.
And the second characteristic is that these problems pop up in all sorts of different real-world contexts.
Exactly. They're not just abstract puzzles. They have practical applications in fields ranging from biology to business to engineering to art.
They even briefly touch on the discrete Fourier transform, or DFT, which sounds pretty complex.
It is a bit more on the mathy side, but it's actually a really powerful tool. It's used in all sorts of things, from signal processing to image compression to even multiplying really large numbers quickly. And the chapter mentions that there's a very efficient algorithm for computing the DFT called the fast Fourier transform, or FFT, which is so important that it's even built into the hardware of a lot of modern computers.
So we've talked about algorithms, the steps for solving a problem, but the chapter also introduces the concept of data structures. How do those fit into the picture?
Well, you can think of a data structure as a way to organize data. It's like having a filing system for your information. And choosing the right data structure, that's a really important part of designing efficient algorithms. Because if your data is organized well, it's much easier and faster to access and manipulate.
So it's like if you're looking for a specific file on your computer, it's much easier if you have a well-organized folder structure.
Exactly. A good data structure can make a huge difference in how fast and efficient your algorithms can be.
Now, from what I'm gathering, this book isn't just going to give us a bunch of pre-made algorithms. It's also going to teach us how to think about designing our own algorithms.
Absolutely. The chapter makes it clear that this book is about more than just memorizing specific algorithms. It's about learning the fundamental techniques and principles of algorithm design so that you can come up with your own solutions to new problems.
And it's going to teach us how to analyze those algorithms to see how efficient they are, right?
Oh, for sure. Analyzing algorithms is crucial because it allows us to compare different approaches and choose the best one for a particular situation.
Makes sense. You don't just want to know that an algorithm works. You want to know how well it works.
Exactly. So the book goes into techniques like divide and conquer, where you break down a complex problem into smaller, more manageable subproblems, and dynamic programming, where you avoid doing the same work over and over again by storing the results of previous computations.
Sounds very efficient. And it also mentions amortized analysis, which is about looking at the average cost of a series of operations over time.
Right. So instead of just focusing on the worst-case scenario for a single operation, you're taking a more holistic view.
But even with all these clever techniques, the chapter acknowledges that there are some problems out there that are just really hard to solve efficiently.
Yes. They introduced the concept of hard problems, and specifically something called NP-complete problems.
NP-complete problems. Those sound a bit ominous. What makes them so difficult?
Well, for these NP-complete problems, we haven't yet found any algorithms that can solve them quickly for all possible inputs. And it's actually a big open question in computer science whether such algorithms even exist.
So we don't even know if it's possible to solve these problems efficiently.
Right. And what makes it even more interesting is that if you could find a fast algorithm for just one NP-complete problem, you'd essentially have a fast algorithm for all of them. They're all linked together in that way.
That's really fascinating. So if we come across an NP-complete problem, should we just give up?
Not at all. The chapter points out that these NP-complete problems pop up all the time in practical situations. And while we may not be able to find a perfect solution, there are often ways to find good enough solutions.
They mentioned something called approximation algorithms.
Right. Approximation algorithms, they don't always give you the absolute best solution, but they can give you a solution that's pretty close, and they can do it much faster than trying to find the perfect solution.
And they use the classic traveling salesperson problem as an example.
Ah, yes, the traveling salesperson. This one's a classic. Imagine you're a salesperson and you need to visit a bunch of different cities. And you want to find the shortest possible route that hits all the cities and brings you back to where you started.
Sounds like a logistical nightmare, especially if you have a lot of cities to visit.
It can be. And as it turns out, the traveling salesperson problem is an NP-complete problem. So finding the absolute shortest route for a large number of cities, that can take an insane amount of time.
But with an approximation algorithm, you can get a pretty good route in a reasonable amount of time.
Exactly. And that's often good enough for real-world applications.
Now, the world of computing is always changing, and the chapter touches on some of the new frontiers in algorithm design. One of the things they talk about is alternative computing models, particularly parallel computing.
Right. For a long time, the main way we made computers faster was by increasing the clock speed of the processor, but we're hitting physical limits with that approach.
So what's the alternative?
Well, one promising direction is parallel computing, which basically means using multiple processors to work on a problem simultaneously.
So instead of one chef in the kitchen, you have a whole team of chefs all working together.
Exactly. And to make the most of these parallel systems, we need to design algorithms that can be split up into smaller tasks that can be executed in parallel.
So you need to divide up the recipe in a way that makes sense, right?
Precisely. And the chapter mentions that the book will go into more detail about these parallel algorithms later on.
And then there are what they call online algorithms. What are those all about?
Well, online algorithms are all about making decisions as information comes in, rather than having all the information up front.
So it's like navigating in real time, right? You don't know what traffic will be like down the road, so you adjust your route as you go.
That's a great example. And online algorithms are used in a lot of different areas, like scheduling tasks, managing network traffic, even things like deciding which ads to show you on a website.
Okay, so we've covered a lot of ground here. We've talked about what algorithms are, why they matter, all sorts of different types of algorithms, even some of the challenges of algorithm design. But the chapter ends with a really important point. It talks about algorithms as a technology.
Right, and this is where they drive home the point that algorithms are not just some abstract mathematical concept, they're a fundamental building block of modern technology.
And even with all the advancements in hardware, in software, in things like artificial intelligence, algorithms are still crucial.
Absolutely. You could have the fastest computer in the world, but if you're using a bad algorithm, it's still going to be slow. And a good algorithm, it can sometimes make a slow computer seem fast.
That's a powerful statement.
Yeah.
And they give this really compelling example comparing two different sorting algorithms. One is called insertion sort and the other is called merge sort.
Yeah, those are two classic sorting algorithms. And insertion sort, it's pretty simple, but it can be slow, especially when you're sorting a lot of items.
And merge sort, that's the more efficient one.
Right. Merge sort uses a divide and conquer strategy to break down the problem into smaller pieces, and that makes it much faster for large data sets.
And they actually quantify this by looking at how long each algorithm takes to sort 10 million numbers.
Yes. And on a really fast computer, insertion sort takes over 5 hours.
Over 5 hours.
But on a much slower computer using merge sort, it takes less than 20 minutes.
Wow. So the algorithm is actually more important than the raw speed of the computer in that case.
Exactly. And that difference, it just gets bigger and bigger as the amount of data increases.
So the takeaway here is that algorithms are essential, even in this age of advanced technology.
Right. And the chapter emphasizes this by pointing out that even seemingly simple applications, like a web app for booking travel, rely heavily on algorithms behind the scenes.
Right, like algorithms to find the shortest routes, to display maps, to even figure out addresses.
And those are just a few examples. Algorithms are at play in every aspect of the digital world.
And what about machine learning? I mean, machine learning systems seem to be able to solve problems without us explicitly programming the steps.
That's a great point. And it's true that machine learning is a powerful tool, but it's important to remember that machine learning itself is based on algorithms.
So algorithms are still at the heart of it.
Exactly. And for many well-defined problems, a cleverly designed algorithm can still outperform a machine learning system in terms of speed and efficiency.
So it's not a case of algorithms versus machine learning. They actually complement each other.
Right. And as computers become even more powerful, and as we tackle even bigger and more complex problems, understanding algorithms is going to become even more important.
It's really a foundational skill for anyone who wants to work with computers in a meaningful way.
I couldn't agree more.
So, to sum up our deep dive into this first chapter of Introduction to Algorithms, I think it's safe to say that algorithms are much more than just some obscure academic topic.
They're a fundamental technology that's shaping the world around us, whether we realize it or not.
They're the engine driving innovation in fields ranging from medicine to finance to transportation to communication and beyond.
And as technology continues to evolve, understanding algorithms is going to become even more crucial.
It's really about seeing the world through an algorithmic lens, understanding the power of computational thinking. And as a little thought experiment, take a moment to think about some piece of technology that you use every day. Could be your smartphone, a social media app, a video game, anything. Now think about what algorithms might be essential to making that technology work. It's a fun little exercise to get you thinking about the hidden world of algorithms all around us.
And this first chapter, it's just the beginning of our journey. We've laid the foundation, and now we're ready to dive deeper into specific algorithms and explore the incredible things they can do.
I'm really excited to keep exploring. And with that, we can confidently say that we've covered all the key points, the main theories, the interesting findings, and the illustrative examples presented in the entirety of Chapter 1 of Introduction to Algorithms, 4th edition.
We did it. Chapter 1 complete.
Thanks for joining us on the Deep Dive. We'll see you next time for another exciting exploration of the world of algorithms.
See you then.